Welcome to part one of our second case study, where we show how to apply key operators from the Project Reactor's Flux class. These operators have been covered in earlier parts of this lesson and the previous lesson, and we show how to use them to create large, random, big integer objects, and then asynchronously check if these objects are prime in a background thread from the default parallel thread pool. We also show how the mono from runnable operator can be applied as well. You can find this example and the source code enclosed in the link at the bottom of this slide. So go ahead and clone that and follow along as we walk through the code itself. We're now in my IntelliJ project for case study 2 of the Flux class. Let's start by taking a look at the ex2 file, which contains the main entry point into the test program. As always, we're going to register several methods with the async task barrier framework. The first method, which is what we're going to talk about in part 1 of this part of the lesson, is the test is prime timed method. And this tests to see whether a stream of random big integers are prime using an asynchronous time-driven Flux stream. There's also a second method called test is prime async that we'll talk about in part 2. As always, we use the async task barrier to run all the registered tasks. They run in background threads, and then the main thread will block waiting for the results to be completed. And then it goes ahead and prints out the number of tests that were run. The real interesting parts, however, occur over here in the Flux EX class. So let's go ahead and take a look at some of the fields in this class. The first field is S max value, which is set to 10 million. And that's the maximum random number value that we can have to check whether it's prime or not. We then have another field called S max iterations, which is set to 10. That's the number of values that we generate in order to be able to do the tests. We have another field called S lower bound, which is the starting point for randomly generating these large numbers. And what you can see here is we take the max value, which is 10 million, and we subtract off the number of iterations, which is 10. And everything between that number and the max value are the values that we can generate randomly. And you'll see why we do that. The goal here is to be able to have a number of duplicates generated. The reason we want to have the duplicates generated is because we're going to showcase something called a memoizer cache, which is implemented here as a concurrent hash map. And this is used to map candidate primes, which are the keys, to their smallest factor if they aren't prime, or 0 if they are prime, which are the values in the map. And you'll see how that gets used to avoid having to recompute whether or not a large number is prime repeatedly. Let's now go ahead and take a look at a couple more fields. We have a random number generator field called sRandom, that's the random number generator. We have a field called sleep duration, which is a duration object that will indicate how long the Flux interval method should sleep between emitting out values, and it's going to be set to half a second. And then the two final fields are a predicate and a function, respectively. The predicate is called only_odd, and that's used to define matches that are only odd numbers. So this particular predicate will return true if the value you give it is odd and false otherwise. And we use that to get rid of even numbers because there's no reason of checking whether even numbers are prime because they certainly couldn't possibly be prime. And then the final field, which is this function, is called sGenerateRandom big integer. And you can see what it does is it uses the value of factor method of big integer to create a random number between the lower bound and this random value that's between 0 and 9, including 9. And so that will basically let us go up to the max size. So that's the window of values that we can generate randomly. Let's now go ahead and take a look at the test is prime timed method. This is what we're going to focus on in part 1. We'll take a look at another method in part 2. As I mentioned before, this method tests a stream of random big integers to determine which values are prime using an asynchronous time-driven Flux stream. It uses a string buffer here to keep track of the string of output we're going to present when we're all done. And we use a string buffer because some of the processing will be done in the foreground, some will be done in the background. And we want to make sure that we don't have problems with race conditions, which would occur if we used a string builder, which is not thread safe. We also define a local variable called log big integer that just prints the value of the big integer to the string buffer. Here's the main outer flux. This is a Flux stream, and we create the stream by using the create factory method. And this will create a flow of random big integers that are generated at a periodic interval in a background thread. And this background thread and the generation therein is done by a helper method called make timed flux sync. So this is a factoring method that bridges the world of reactive programming, which is where we want to live most of the time, with a callback style world by emitting a time-based flow of random big integers at a periodic interval. So let's take a look and see how this is done. You can see that make time flux sync returns a consumer that's parameterized with a flux sync, which is parameterized by a big integer. So here we go. We take a look here, and here's the inner flux stream that we're generating. And we use the interval method to generate a long stream starting at 0 periodically in a background thread. And this background thread comes out of the default parallel thread pool. And you can see that we sleep for S sleep duration time, which in this case is half a second. And so that will generate these long values starting at 0. Now, we're going to have to turn those long values into something useful, or actually not turn them into something useful. We're going to ignore the values and just use the fact that we're getting a pulse or a heartbeat every half second to then use the map transforming operator to generate a random big integer. And you'll recall that generating the random big integer is a function that will generate the values between the lower bound and the max value. So that will then put out these random big integers within the range that we want. We then apply the filter suppressing operator to get rid of anything that's not prime. There's no sense in checking even numbers to see if they're prime, because they won't be prime because they're divisible by 2. Then we go ahead and use another suppressing operator called take. Remember, interval will go on forever, but we only want to take up to S max iterations of these values. So we're not going to go any further than that. We're just going to take up to 10 of these things. And of course, we could also have been filtering out the ones that were odd. So now what we're going to do is we're going to go ahead and call the subscribe terminal operator, and that has 3 parameters. The first parameter is the signal that's emitted when everything goes fine. So we just go ahead and send another random big integer up to the rest of the stream. If there's something that goes wrong, which shouldn't happen in this case, but if something goes wrong, then we go ahead and say we're done. And when we reach the end of take, then we go ahead and send the complete event as well. That says we're finished emitting values. So let's now go back up here to the create method, which is getting back this stream that's running in the background, and see what it does in response. So what it does in response is it then goes ahead and runs these other methods or these other operators here. Keep in mind that all of these operators are running in the context of that thread that's the default parallel thread pool thread, the one that interval is using. So everything's running in a single background thread. And you'll see that when we actually run the program and look at the results. So what we're going to do now is go ahead and log the big integer just so we can see what it's doing. And then we do the real interesting part. We go ahead and apply the map transforming operator to check to see if the big integer is prime or not. And here is the check if prime method. This is a pretty interesting method. It checks to see whether the parameter called the prime candidate is prime, and that's the number that was generated randomly. And what it returns is a prime result object that contains the prime candidate, which is the number we were looking for, and either 0 if the number is indeed prime, or the smallest factor if it's not prime. So let's take a look and see what we do to make this work. This is pretty interesting, and it shows off some cool, more recent Java features. The first thing we're going to do is we're going to create ourselves an instance of a record called prime result. Let's go look at prime result. Prime result is a Java record, which is a fairly new Java data type that holds plain old data. And in this context, that means it's just the fields and nothing else. In contrast, regular Java objects contain other information, such as the v pointer that points to the virtual table that holds the virtual methods, such as a monitor lock that can be used for synchronized methods, such as the monitor condition that's used for wait and notify, and so on. So there's a bit of extra cruft that comes with a regular Java object. In this context, we just want plain old data. So we go ahead and use a record. And the record has 2 fields, the prime candidate, which is the original number, and then the smallest factor, which could be 0 if the number is prime, if the prime candidate is prime. Notice the syntax for making a record. You have what looks like a method call, but this is the first field and this is the second field. They're actually fields, not parameters. And then we have to put this kind of funky syntax at the end, at the open close curly brace, just to indicate that that's the end of the record. Don't ask me why they had that syntax. You'd have to ask the Java designers. It was probably to make the grammar more coherent and less ambiguous. So that's the prime result method. Let's go ahead and come back over here, or rather the prime result record. And you can see that we give it the prime candidate, and then the smallest factor value comes from invoking a very special method on our concurrent hash map, S prime cache. And this method is called compute if absent. And it's what's commonly referred to as an atomic check then act method that serves as a so-called memoizer cache. So what we're doing is we're memoizing whether or not number is prime and associating it with the number itself in the hash map. And the way that compute if absent works is if the prime candidate already has a value, that means we already have pre-computed or we have already computed what the status of that particular prime candidate is with respect to its primeness. Is it prime or not? So in that case, if there's already a value, we just return the value. There's no need to recompute the prime number. But the first time in, there is no value associated with that key. So we're going to have to call the isPrime method. And isPrime is a method that does a brute force determination of whether the prime candidate is prime. And it returns 0 if it's prime, or the smallest common factor if it's not prime, or smallest factor. As you can see here, what it does is it first just does a little sanity check to get rid of even numbers because they're not going to be prime. And then it runs this loop, which is intentionally designed to be inefficient, just to burn CPU cycles, to make it counterproductive to have to recompute prime numbers over and over again, thereby motivating the need for caching them. And this goes ahead and will try to find the smallest factor. Otherwise, if it can't find a smallest factor that divides evenly, it will go ahead and just return 0, indicating that the number is indeed prime. So coming back over here, you can see that that'll be stored the first time in. We'll store the key's value, which will be whether it's prime or not. And henceforth, if there's a duplicate, we'll just look it up and it'll take much less time than having to do the recomputation again. So that's what we do for check if prime. Then once we pass this test, we get a flux of prime results. Notice how map can transform its parameters. So it took in a big integer and it returns a prime result for each of the big integers that came in. And then we go ahead and we do on next, which remember is this action operator that has a side effect only. And this side effect is to call the process result method. And you can see what that does is it goes ahead and takes the prime tuple and checks to see whether or not it had a 0 value, which means it's going to be a non-prime, because we're going to use the negate operator. So if we find a non-prime number, we print out its smallest factor. Otherwise, we say we found a prime number and we print that value out as well. So that's just a little way to do some diagnostic output. The final method that's in our Flux stream is the then method. And you recall, then is kind of interesting. Then does two things. First, it can go ahead and call this particular operation. And what we're going to do here is we're going to use the mono from runnable operator to go ahead and trigger the printing of the string buffer by converting it into a string and then telling it to display itself. And if you look at display, it just prints out on the console the current thread ID and the string that we have been building up as earlier parts of the processing in this Flux stream. That will then go ahead and trigger, get run, the from runnable method, and then returns an empty mono, which is used to synchronize with the async task barrier to tell it everything's done and you can go ahead and you can basically essentially shut yourself down when other asynchronous operations complete. So armed with this information, now it's time to go ahead and actually run the program and see what output we get. So as you may recall, if you take a careful look at the program, the first thing that we do is we run the method called test is prime timed, which is what we just looked at. And then we run the test is prime async method, which we're going to look at in the second part of this video. Interestingly enough, test is prime async finishes first because it's not doing timed operations, where test is prime timed is doing prime timed operations. And you can see what happens. You can see that all these processing steps that we're printing out here are taking place in a single background thread, which comes out of the default parallel thread pool. So it's parallel-1. That's created for you by the underlying Project Reactor schedulers framework. And then you can see that in that one thread, we're emitting a random number within the range that we designated, and we're only going to emit things that are prime, because if they're only emit things that are odd. We're going to emit odd numbers only and ignore or filter out all the even numbers. Then we go ahead and we run that is prime check, and you can see we found a prime number with the smallest factor 7 for this value. Then we emit another thing that requires us to check to see if the number is prime. And you'll also notice, because of the way we share that particular memoizer cache, that it was also being leveraged by the other threads that were running in the background too, which is why we used a concurrent hash map. So sometimes we have to explicitly check to see if a number is prime, but then other times when we emit the same value a second time, then it doesn't have to be recomputed. So notice we emit this value once, we had to do the actual is prime check. That gets stored in the concurrent hash map. And then the next time we emit the same number, so it's a duplicate, this time we don't have to do any checking. We just go ahead and look it up in the map and it's right there. So that's the benefit of using the memoizer. And you can see that we emit a bunch of different numbers. They're all odd numbers, of course. Some of them are duplicates, some of them are not. And this prints out the results. And you'll also notice, if you look very carefully at when things are sent off, that they're going to be emitted essentially every half second. So it gets emitted here, and then a half second later it gets emitted there, and then we emit again, and then a half second later we emit again. So this is basically working using the mechanisms that we get from Flux interval in order to have sort of a pulse or a heartbeat to emit the values every half second. So that's the end of our first part of this case study 2. We're going to take a look at part 2 next.